Hi. In this presentation, we will look at the specification proposed for the first part of our compulsive coursework plan, which addresses the implementation of an electronic dice supporting various types of sheeting. After watching this presentation, I hope that you will be able to explain the functional specification in your own words, and also to identify the main design tasks that you have ahead, and finally also that you will be able to set up a plan to reach a working solution. And here's a list of the functional requirements that have to be addressed. We will need a running mode that takes the e-dice through the 6 possible results very quickly until the stop button is pressed. We will also need 2 mode inputs that will be used to specify the sheeting mode, and 3 result inputs which will be used to specify any possible e-dice result. These inputs can be used, for example, to specify that result 5 should never happen. And we will need 2 types of outputs. We will need a set of LEDs to represent the dots in the dice, and also a 7-segment digit that will be used to display the result in decimal form. And here you can see the 4 default assumptions that you must keep in your mind when carrying out this work. To start with, please recall that all the LEDs that you have available above the switches light up when driven to logic 1. Also, we may assume that each of these LEDs, which we can use to represent the dots, will have their own driving pins. Well, in fact, this wouldn't be necessary because 4 outputs would be sufficient to drive the 7 LEDs. And this happens because 6 out of those 7 LEDs light up in pairs. For example, the top right LED always lights up together with the bottom left LED. In what concerns the digits, please bear in mind that each segment lights up when driven to logic 0, so it's opposite as to the LEDs. And finally, please keep in mind that we normally assume that all inputs are active high, and this applies both to the switches and to the push buttons that we have available on the board. Now, this slide shows a summary of the operating modes that shall be enabled by our 5 inputs, the 2 mode switches and the 3 result switches. Notice that we have 1 no sheeting mode, which is selected when the M inputs are both 0, and 3 sheeting modes. When the M inputs are driven to 0, 1, then the pattern driven to the R inputs will be used to specify the forbidden result. On the contrary, if the M inputs are driven to 1, 0, then we will have selected the predefined result mode, and in that case the combination driven to the R inputs will specify the result that shall always come out. And finally, if we drive both M inputs to logic 1, then we will be in the triple probability mode, where the result specified by the R inputs shall have triple probability when compared to all the other results. Now, the LEDs that we have available in the board are laid out in a single line above the switches, as you may remember, so they will not replicate the position of the dots in the real dice. But we can use those LEDs anyway in order to simplify our work. And in that case, we will have to complete a table like this so that we can easily figure out the result by looking at the pattern that is displayed in those LEDs. Notice that we are using the same names as in the original constraints file, and that's good to minimize the editing work that you will have to do on that file in order to allocate pins of the FPGA to our inputs and outputs. Now, this slide shows the allocation of board resources, that is to say, of the switches on the right to the mode and result selection inputs, of the push button on the right to the stop button, of the right wing of LEDs to the dots in the dice, so-called, and of the rightmost digit to display the result in decimal form. Please follow this recommendation in order to simplify my task when checking the outcome of the work of the various groups. Now, this coursework project becomes a quite simple task once you have designed this state diagram for the finite state machine. That is actually the only difficulty I had, since the translation of a state diagram or an ASM chart into a corresponding VHDL description is a very straightforward task. But since that is the main difficulty I had, I leave you this recommendation. Start small. Design a state diagram for a very simple no-cheating e-dice that goes through the 6 possible results in sequence until we press the stop button, no more than that. And then make it progressively more complex by adding additional inputs as I indicated here. Starting small will give you confidence and help you to understand the way forward as you expand into more sophisticated cheating options. You may, of course, choose your own roadmap, but here's one possibility. Gather the group together to think about the state diagram, and then split up to work separately on building up the VHDL descriptions, and get together again to compare your results after compilation and simulation, and then split up once more to carry out the final parts of the work for each of the stages shown in the previous slide. That is to say, to allocate pins, generate the bitstream file, and then experimenting in your own basis 3 boards. And of course work together on the preparation of your presentation, which is a very important part of your deliverable together with the Xilinx project folder. And that's it. You are now ready to start your work. I hope that you will enjoy this assignment and learn a lot during these 2 weeks. Thank you.